Hello, I'm Kukhyun Kim. This study is an ongoing study and part of my lab project. This study is about measuring multimodal data in XR-based training simulation environment. XR-based training simulation has gained popularity recently due to their ability to provide immersive and interactive learning experiences. XR-based training simulation allow for realistic and a safe training environment that may be difficult or dangerous to recreate in the real world. In addition, XR-based training simulation can be customized to the individual learner's needs and preferences, such as their own pace and the level of expertise. In addition, XR-based training simulation can provide immediate feedback to learners, improving learning outcomes. Another advantage of XR-based training simulation is they can be more cost-effective and time-efficient. Furthermore, XR-based training simulation can provide opportunity for remote learning and collaboration. It is important to assess the learner's performance in XR learning environment. By understanding learner's performance, immediate feedback can be provided, which can aid in predicting and evaluating learning outcomes and learner's state. Multimodal information such as brain waves, eye gaze, and facial expressions and heart rate, the sweat, time, and performance behavior, all these things can provide learners with information they may not have been aware of during the learning process and offer insight into their cognitive and emotional state at the specific moment. Multimodal data is increasingly used in the learning analytics to gain an insight into learners' behavior and performance in education settings. For example, eye tracking and facial expression data has been used to identify pattern of learners' behavior that indicate engagement, interest, or understanding of material, as well as their cognitive role in attention. In addition, mouse movement in a clicking stream in a video recording and self-reported feedback can be used to recognize learners' behavior and performance in learning analytics. Psychological data such as heart rate and skin conductance can be used to evaluate learners' stress level and emotional state. Head position or data also can be used to identify users' level of engagement and attention. And hand movement data can be used to evaluate the user's motor skills and proficiency to evaluate learners' proficiency in surgical procedures. Based on these previous study, this study investigates various multimodal information sources that can be utilized to determine the learner state and proposed future study direction based on these findings. The research goal is to investigate the potential of multimodal data in predicting the user's performance in an XR-based training simulation environment. The participants are 22 medical residents in South Korea, 14 males and 18 females. The average age was 25.6. The repeated within subject design was used, and all participants experienced 3 scenarios tasks of XR-based training simulation. This is XR-based simulation we used. This simulation called the SIMSEA, aimed to diagnose pediatric patients with strabismus using holograms. Participants examined the virtual patient and diagnosed strabismus by evaluating change in the eyes. Strabismus diagnosis simulation comprised 3 scenarios, and each process are shown in the following 3 figures. Firstly, the ocular motility was performed with a stick to test the participant eye movement. And the second, the cover-uncover test was conducted to diagnose strabismus and the type of strabismus while covering the eyes. Finally, the prism test was performed to diagnose the degree of strabismus using a prism. In particular, the rear prism tool could be practiced for holding the prism tool with correct posture during the prism test. As you can see the upper figure, when using the prism, the backside of the prism had to be perpendicular to the patient's visual axis. Otherwise, the patient angle of view could be diagnosed incorrectly. Each scenario lasted between 2 to 3 minutes to complete. Table 1 shows the type of multimodal data and variables collected. Gaze information and the head position of the user were used to measure the user's attention and cognitive load. The head position and interaction with a 3D object was used to check the accuracy of diagnostic performance and skills. Figure 3 shows the process of data collection. Figure 3 shows the hands, head, and gaze data was extracted using HoloLens Pro 2. And in addition, object interaction data was extracted using data from the participant interacting with a real object. All the multimodal data was extracted at the rate of 30 times per second. Table 1 shows the extracted multimodal data and the number of categories: head position, head rotation, head tracking. Gauge data include a total of 12 sub-factors and a gauge origin, gauge direction, gauge hit position, and a gauge hit normal. Hand data consists of 98 hand joint position, and object data include 9 sub-factors: stick rep valid, and the stick rep try number, stick rep try time, cover grip valid, cover grip try number, and then cover grip try time, and also prism grip valid, prism grip try number, and prism grip try times. And this study proposed using multimodal data extracted from the head gauge and hand and object interaction to identify cognitive load, attention, and performance level in XR-based training simulation. Multimodal data can confirm the information such as how much the user pay attention to the learner task during the training process, the level of cognitive load experienced by the user, and accuracy of a user's performance in skill training with target skill object. The result of the study could be expected to provide baseline data for the development program.